Multivariable calculus. This contains gradient, divergence, and curl. So let's start from the basics. First of all, partial differentiation. So here's the definition of this thing. So for a function f which is of x, y, and z, these are our free variables. You could have more variables as well, but usually we will just have three because 3D space. But right, so f of x, y, z, if that's a function, then partial f upon partial x, that is given by this limit. So it's the limit as h tends to 0 of f of x plus h comma y comma z minus f of x y z upon h, right? So this is the derivative of f with respect to x while keeping y and z constant. So for example, if you had f equal to x y z, then partial f upon partial x would just be y z because they would behave as constants. If this was x y z plus y square, then partial f upon partial x would still be y z because y square is a constant. Fine. There's this nice property for partial differentiation that for nice functions, partial differentiation is commutative. So partial upon partial x of partial upon partial y of f, that is the same thing as partial upon partial y of partial upon partial x of f. So here's a small, let's just say, informal proof of this thing. It is not that rigorous, but yeah, you can read that, and it's honestly not that enlightening or anything. It's just a normal proof, right? Multivariable chain rule. So if a function f of x y z can be expressed as g of u v w, so this function is expressible in some other free variables. So for example, you have the Cartesian coordinates, then you can go to the spherical coordinates, and those would be our UVW, right? So instead of UVW, you just have r, theta, and phi. And then the thing is, UVW and XYZ, they should be linked by a bijective transformation. So for example, the Cartesian coordinates and the spherical coordinates, those are linked by a transformation that is bijective. So you can go from one way to other, right? If you know all of XYZ, you can figure out all of r, phi, and theta. And similarly, if you know all of r, phi, theta, you can figure out what XYZ must be. There are no two ordered pairs of two ordered lists of UVW that you should get for a single XYZ. That should never happen. So that's why bijective, and it should be both ways. So yeah, okay. So these are linked to each other by a bijective transformation. So transformation in this context is just a vector valued function in XYZ which gives our UVW. Then changing only u by amount du will change XYZ by these amounts dx, dy, and dz. Well, they are given by this thing: partial x upon partial u times du, and partial y upon partial u times du, and partial z upon partial u times du, right? But under any circumstance, so even if you were not just changing you were doing all kinds of crazy stuff, in any case you can write df is equal to partial f upon partial x times dx plus partial f upon partial y dy plus partial f upon partial z dz, because given x, y, z, you can completely figure out the value of f. There's no need for any other variables, right? And well, in that case, the contributions for this complete change in our f, well, those come only from x, y, and z. So you change x a little, your f changes by this value. You change y a little, your f changes. Your change z a little, your f changes. And then in the neighborhood of our xyz point, the rates, so partial f and partial x and all these all these coefficients, well, they are the same, right? Or I should say approximately same. So you can first change by x, then by y, then by z, and you will add all of these changes and you will get the final change in this way, right? But now what we can do is replace dx by this thing, because now we're only changing u, so you can write dx like this, and now replacing this, you just get partial f upon partial u is equal to partial f upon partial x times partial x upon partial u plus partial f upon partial y times partial y upon partial u plus partial f upon partial z times partial z upon partial u, right? So that du I just divided by that thing, right? So dx will have this thing, that du you can put that out, right? Take that common from these three terms and then divide by du, you'll get this thing, and it should be df upon du on the left hand side, but then since you're only changing u, it's basically partial f upon partial u, right? Also, this can be written in this way, which you don't have to worry about right now. It's just some shorthand notation. Okay, right. We go to this notation now. It's the del notation. So del or del vector, I like to write like that. This is given by this sort of vector kind of thing, although it's not exactly a vector, it's an operation or something that's used to define operations. So it's this thing, x hat partial upon partial x plus y hat partial upon partial y plus z hat partial upon partial z. So this is used to write short notation for operators like gradient, divergence, curl, etc. So for example, just the del applied on a scalar function f, that would be our gradient, and that's basically this thing, partial f upon partial x, partial f upon partial y, and partial f upon partial z in the x, y, z components. Yeah, that's a vector valued function, vector valued operation, I should say, whatever. Then here you have divergence, so it's del dot u, which is, yeah, just works like a dot product. And then you got the cross product, this is the curl. Then you have this thing, this is the material derivative or something, whatever. So you can use del to write these operations in a short form, right? Next we have the gradient. So the more abstract definition of the gradient, well, that's given by this thing. So for a scalar valued function f x y z, the gradient, which is del f, it has the property that df upon dr is equal to del f dot r hat for every r hat. So first of all, let me explain what all these symbols mean. Dr is the amount of distance you travel along r hat, right? So imagine you are at a point x y z and you nudge to some direction. So in r hat you move by a dr amount, which is a very small amount. You move in a straight line, of course, and that movement causes a change in your f value. So the ratio of these two changes, df upon dr, is basically the rate of change of f with respect to the distance traveled, right, in that particular direction, r hat. That's what this thing is. It's just df upon dr, that's equal to gradient of f dot r hat. So gradient is a vector valued function such that this happens for every r hat or for that point x y z. All right, so you can set r hat to be I hat or x hat if you want, and basically get the x component of gradient of f, and then similarly set it to be y hat and z hat and get the yz components, and there you go, you got the final formula for gradient, which is just partial f upon partial x, partial f upon partial y, and partial f upon partial z, right? So partial f upon partial r is the directional derivative. Yeah, well, actually that should be the thing. So instead of writing partial f upon partial r, I should just say df upon dr, because there is nothing else that we could care about, right? It's only the distance that we are talking about, right? So df upon dr, this is the directional derivative. So it is maximum when r hat is along our gradient. Thus gradient points in direction of maximum increase in f. So for a function f of x y, so it's a function on these two variables x and y. It gives a scalar. So you can graph this as the z coordinate, right? And when you will graph this, you just get a surface. So for some certain point x y z, the magnitude of this vector gradient f, that gives the largest value of the slope of a tangent to the graph at that particular point, right? So you will have different kind of tangents, right? You will have a circle full of these tangents. Then the tangent which has the biggest slope, and the slope is of course the rise over run, and the run will be the distance along the xy plane, and rise is of course the distance moved in the z direction, right? Yeah, so that slope, the largest value of that slope, that's given by this thing, the magnitude of gradient of f, right? Next we go to divergence. So for a vector valued function u vector of x y z, the divergence del dot u at a point is given by this limit. So it's a very abstract definition. Usually the way they define it is just the formula, but I'm actually going to define like that so that I can later on use this to prove some theorems, right? So we have this thing, del dot u, that's equal to limit as v tends to 0 of the integration over a surface of u vector dot dA vector upon v, which is the rate of change of flux for that volume. I mean, you should say the boundary of that volume with respect to the volume itself. So what what are all these things? Well, S is the boundary surface of a volume V, and the volume V contains our point of interest, which is xyz. The numerator, basically this integral, this is the flux of u vector through the surface. Okay, so now let's take a special case. So for a box of dimensions delta x, delta y, delta z as shown, our flux in the x direction, so basically the flux through the two walls perpendicular to x hat, right, that is given by this thing. So it's the integration of u vector x plus dx, sorry, x plus delta x minus u vector of x. So why am I omitting y and z? Well, those are changing. Y and z are changing as you move through this surface, right? And that's inside an integration. So it's supposed to be a function of y and z as well, but then this can approximately be written as partial u vector upon partial x times delta x, which yeah, it doesn't change a lot because this delta x, delta y, delta z stuff, this is actually very small, so you can approximate it like that. It's legit. So then this integral, well, this just becomes this thing, partial ux upon partial x delta x, and that times delta y delta z. So of course it should just be the x component of this guy because the dA vector is in x hat direction and dA is just the magnitude. So yeah, our flux in the x direction, that just becomes this thing, partial ux upon partial x, that times delta x, delta y, delta z. Now delta x, delta y, delta z is the volume of this box. So now adding all of these fluxes together from the x direction, from y direction, from z direction, and dividing by volume, what you basically get is just this thing, partial ux upon partial x plus partial uy upon partial y plus partial uz upon partial z. And yeah, this is our divergence. So del dot u. Okay, so we have the divergence theorem, which we can prove from this very definition of the divergence. So for a volume made by two adjacent volumes, the new flux is the sum of the old fluxes. So you have this figure showing what's exactly going on with the flux. So for these two volumes, you can break the flux as the contribution from the surfaces which do not coincide and the contributions from the surfaces which do coincide. So these red and blue surfaces, well, they have opposite flux, they are coincident, their area vectors are opposite, so that's why the flux through them is also opposite. Addition is 0. And then these surfaces, the green surfaces which do not coincide, well, we just combine them to form this new volume or the surface of the volume, right? And the flux through that is exactly just phi 1 dash plus phi 2 dash, right? So that is by definition just that, and the phi blue plus phi red thing is just 0. So you can write phi 1 plus phi 2 equal to phi 1 dash plus phi 2 dash. So basically phi 1 plus phi 2 equal to phi 3, where phi 3 is the flux through this new volume, or I should say the flux through the surface of this new volume. Well, whatever. So now using this fact, what you can do is basically integrate our flux through infinitesimal volumes, right, and add all of these fluxes together, and the net flux that you will get, that will be the flux through the boundary of the final volume you have got, right? So basically the flux through the surface of any volume, that is given by the integration of d phi, where d phi is the flux through an infinitesimal volume. But now you know that you can write it like divergence of u vector, well, that times dv, right, by definition. Basically the integration of that, and from that you get this theorem that the integration over the volume of divergence is equal to the integration over the surface of our u vector. So yeah, the area integral. Cool. Next we have the curl. So this is written by del cross u. So this is a vector such that del cross u dot a hat is equal to limit as a tends to 0 of the integration over a path basically over a loop of u vector dot dl vector upon a, where the integral is done over the boundary path of a surface with area A. A hat is given by the right hand rule applied on the path. The equation must hold by definition for any A. So this equation must be true for any A hat, and then the value that has this true for any A hat, that is what we call the curl, right? So that is basically the definition. Till now we are not finding it yet. Now we start to figure out what this should be. So if this is true for any kind of A hat, then this should also be true for A hat equal to Z hat, right? So for this rectangular surface along the xy plane, you can write this integral as this thing, which you can approximate like that. It keeps on going, and finally what you get is this thing, partial uy upon partial x minus partial ux upon partial y, that times the area. That's what this integral is. Divide by the area, just get partial uy upon partial x minus partial ux upon partial y. And yeah, that's only the curl dotted with z hat, so that's only the z component, and you have to figure out the xy components also, and what you get finally, right, combining all these components, of course along with the unit vectors, is basically this thing. The curl is given by this, so it's of course a cross product between our del and u vector. Yeah, but we haven't proved that the initial equation is true for any a hat if this is the curl. So if this is the curl, this should be true for any a hat, right? Because that's how we define the curl. So if this is not true, then there's no point in making such definition. Okay, so let's try to prove that this is really true for any a hat. Right now it's only for x hat, y hat, z hat. The original equation is the same as this thing, right? So just move that dA on the left hand side, and let's not think about the limiting case, let's just think of it as an approximation. So del vector crossed with u vector, that's our curl, of course. So curl dotted with a hat, the a vector, now it's having dA as well, so now it's a vector, not a hat, dotted with a vector, that's equal to this integral. So it's the integral of u vector dot dl, right? And this is true if a vector is small. Taking a projection of the surface on xy plane, we get a new surface for which the equation is true. So we already proved that this should be true for all the cases where your surface is on the xy plane or on the yz plane or on the xz plane completely, right? Then it's true all the time. You already know that. So now it's one of those cases that it's on the xy plane. We already proved that, so we can write this equation for that particular path and surface. So you get the first equation that way, and similarly you can project it on other planes and you will get these two other equations. Now adding all of these equations up, you basically get this equation that we wanted to prove, right? And that should have been true if it really is like that. Okay, so basically what we get is that the curl dotted with a vector, that's equal to or approximately equal to this integral, so the closed loop integral of u vector dot dl vector, right? So the equation is really true. Okay, and a trivial consequence of this is Green's theorem. So you have this equation, but you can write this in a more differential form. So you can say that a surface is basically made up of a bunch of surfaces, like infinitesimal surfaces, and the paths of those surfaces, like the boundaries, of course, wherever they coincide, just like we saw for divergence theorem, in the same way the parts where they coincide, the integral, well, that cancels in those parts, right? And so basically the final boundary that you have to be dealing with, that's just the boundary of the final surface that you will get, right? So a consequence of this thing is Green's theorem, which says that the integral of the curl, right, dotted with dA vector, of course, over a surface, that is equal to the path integral of u vector dot dl vector, where the path is the boundary of this surface, and this is true for any kind of surface. Alright then, so this was multivariable calculus. I mean, as much as I know right now. I will improve on this PDF soon, and I'll update you. Okay, I'll see you guys next video.